You are very fair. No, it doesn't matter. I don't really need this time, but tomorrow I would need it. So don't bother about any spotlight. As long as Jean is happy, I'm happy. And I know you are very happy because they have very thoughtfully put a very big clock in front of me. And tomorrow I expect to see a grandfather's clock. If you allow me to take it away and also pay the customs duty other end, I don't mind. But I assure you that this session won't be that heavy. I know after lunch everybody likes to sleep. I have just witnessed a miracle, if I may share it with you. And the miracle is the hall is full. I mean, so Swami is doing something around. I didn't expect. I thought half the people would have said, hey, we forgot this is Memorial Day weekend. What are we doing here? But it seems to be, he has brought them here. Let me, before I get started, I assure you this part will be very easy to absorb. But I want to connect what is going to come shortly with what we did this morning. In a sense, it's all about our nature. By that, I don't mean whether you're a good guy or a bad guy and things like that. But the point is, what are we made up of? We are actually made up of three distinct entities. At the gross level, we are made up of gross matter, which the ancients described in terms of 5 elements. But today, we would say we are made up of molecules of different kinds. Then there is a subtle level which manifests as the life force plus our mind. One major aspect of our life force is the mind. So the body next to mind. But there must be an engine that drives the mind and the body. And that engine is the Atman inside. And because this Atman has got a body and a chassis and so on and so forth, it is called Jivatma, as distinct from Atma by itself, which is the God that is eternal, omniscient, omnipresent, who is there whether there is a universe or not. So we are embodiments of that Atma, the embodiment being manifesting in the form of a body, physical body, and senses and the mind. So we have these three things, body, mind, and Atma, MB as Swami used to call it. And the question now is, what is the pecking order, as you say in this country, in management circles? The right pecking order, it's not the right word to use, but the management whiz kids may wake up and then say, hey, he's telling us something, we are getting free lessons on management. Is Atma first, mind next, and body last. If we have it right like this, then the journey of life can be facilitated. What is the purpose of life? Swami said once to boys, he asked, what is the purpose of life? They gave all sorts of reasons, answers. He kept shaking his head. And then everybody stopped because, we tried all answers, we didn't get it. The quiz master won. So then he said very slowly, the purpose of life is to go back to God. From God you have come, and to God you must return. It is not from dust we have come, and to dust we return. He says, no, from God you have come, and to God you must return. And here, I would like to give a small example, which I mentioned yesterday at Caltech. Nature gives many examples of this. One example I'll give you, that is of the fish of the breed species salmon. The salmon is common in America. We don't have salmon in India. It is usually born in the upstream of a river. They have it in the East Coast and also in the West Coast. And then when it grows big enough, it starts going downstream. It comes to the Pacific Ocean where the river merges. At that time, its body chemistry completely changes. You may ask, why? What for? Reason is, the chemistry of a seawater fish is different from that of a freshwater fish, saltwater fish and saltwater fish. So God triggers everything. And then the salmon goes on a long journey, almost up to Japan. They have tracked the arcs and all that. And then at some point, it makes a U-turn and comes back. And amazingly, although there are salmons from different rivers on the west coast, from Canada as well as California and so on, each salmon knows which river it came from. And it goes upstream to the point. It's an uphill task for the salmon to go upstream. I remember when I first went to Canada in 1958, we went to some place and they said, there's a small dam here, this is for salmon to go out. There's a bypass for salmon. And it lays its eggs there and dies. So, just as the salmon goes back to where it came from, we also are supposed to go back where we came from. So what's the problem, you may ask? The problem is simply this. Swami says God is everywhere, and he used to tell us, I am in you, above you, below you, around you. We said, yes, but we never paid attention to what it really means. It means the following, two things. God is inside us, and God is outside us. So inside means what? Is he in the lung? Is he in the this place? No, he is everywhere. And that I shall explain shortly, as Krishna points out. But the sort of centrality of this presence of God everywhere in our body is the so-called spiritual heart. So God is there in the spiritual heart. God is there outside. So God must be continuous. He is, but from our perception, he is not continuous. There's a shutter that prevents us from seeing God outside and God inside are one and the same thing. And what is that shutter? It's our ignorance. That ignorance makes us what you call fail in seeing God inside. It makes us feel seeing God outside. And as a result, we don't see God in other people. And we forget that we are God. We behave like animals or devils, depending on how your gunas are fixed. So, the aim of this part 2, is to talk first about the glory of God. And I say glory of God, I'm going to talk about glory of God as He is present in us, within us. I am in you, Swami says. And I'm also going to talk about glory of God as, can I have the first slide, please? This is the title of this part. Glory of God as He manifests here. And there is something about that which I will mention towards the end. So this is the first slide. Now let's have this next slide. This is again from the Bhagavad Gita, the sloka identification is given there. It's essentially God talking about Himself, God as an avatar talking about Himself as the omnipresent God. He says, those who comprehend my integral being comprising the Adi Bhuta, the all-pervading gross aspect, the Adi Deva, all-pervading divine aspect, and the Adi Yajna, the omnipresent and immanent divinity everywhere, they of steadfast mind are conscious of me even at the moment of death. They never forget me. Essentially, he says, I am everywhere. Now, what does this everywhere mean? That I shall explain. I now go to the next slide, which is very important because right at the beginning of the 8th chapter in the Bhagavad Gita, Krishna asks 2 questions which are flashed there. The first question is, he says, O Purushottama, Purushottama is the ultimate. Or as the former president of India, philosopher Radhakrishnan said, ultimate, ultimate, there ain't nothing beyond that. Ultimate, ultimate. He asks, O Purushottama, what is Brahman? What is Adhyatma? What is called Adibhuta? And what is Adi Deva? O Madhusudana, who is Adi Yajna? How does he dwell in the body? This part of my talk is going to be a sort of amplification of Krishna's answer to those 2 fundamental questions. And the next slide sort of summarizes the essence of what Krishna says. Just to remind you, I have at that level something that I showed in the morning. This is Purushottama or Brahman, call him what you will. And when Brahman creates the universe is created at 3 levels. We see mostly the material level. I see things like this. But hidden above in it is a subtle level, and that subtle level manifests mostly in living beings. And in us, we have an extra layer which allows us to recognize not only the subtle and the difference between subtle and gross, and the fact that this itself has something from some eternity. In other words, this is what helps us recognize the existence of a transcendental entity. So let's see what Krishna says. First is, Krishna's declaration is all about, Krishna explains how God is present at various levels. And for sake of completeness, I should mention that Swami has also talked about these three universes using three phrases. This is for the benefit of those who pay attention to details. This universe is called Bhutakasa. This universe is called Chittakasa, and this is called Chidakasa. Brahman is even beyond that. So, in terms of gunas, this is the iron rope, this is the silver rope, this is the gold rope, but we have to go even beyond if we want to merge with God. And Arjuna has two doubts. One is about God there and the God who is omnipresent here. This is the universe in which we live. We see only material objects, but God is present at this level and this level also. So he says, how are you present here and how are you present here? This question was often asked of Swami. Somebody will describe an experience how Swami appeared in America, and afterwards they will say, Swami, you are in Vrindavan, how are you in America? Which airline did you fly? What flight did you take? Swami says, you people have a very poor, I heard him once say this, you people seem to have a very low opinion about God. And then he said, that somebody speaks in Washington, you are able to see him in Bangalore. If man can do that, can't God be in two places at the same time? Well, that shut up this questioner. Then he said, God is everywhere. He doesn't have to take the American flight or Delta flight. He is everywhere, and wherever he is called, he will make his presence felt or appear. He doesn't have to travel anywhere. I am everywhere. And that's exactly what Swami said. So Krishna, in his reply, explains God is present in the body at three levels, and also in the universe everywhere, and also beyond. Of course, then later on Krishna asks which God to worship. Do I worship God there or God here? So, and Krishna answers that also in the 12th chapter. I made a brief reference to that also. So now we are all set to have a huge change of gear, and be ready for it because this may come as a shock. I'm now not going to talk about spirituality for a few minutes, but talk about the universe in which we live. And then you will know why I'm saying all these things. So if you think I have gone bananas, I ain't gone bananas. But I'm warning you and giving you advance notice. Can I have the next slide, please? I'm going to talk about stars, not movie stars like you have here, but real stars. And then you will know why I'm talking about stars, because you will get to that. Now, what is a star? Twinkle, twinkle, little star, how I wonder what you are, says the nursery rhyme. But for about 150 years, people have been actually wondering what a star is. The first studies in this go back to about 1850, when physicists, largely in England, speculated the star was a gas cloud, which was somehow bright. And they had an explanation of why it is bright. And then they applied some physics as known then, but it was leading to some contradictions. And the man who resolved it at the first level was Eddington of England. I'll mention about him later, in Cambridge, a very distinguished physicist who, by the way, was responsible for planning the experiment that made Einstein into a rock star. So if you want, I will answer that question at the end, because otherwise I'll lose track of time, and Dr. Reddy is already looking at me. Oh my God, this man is wandering here and there. What is going to happen to the clock? Is he about time? Is he God? Even Swami bowed to time. Don't worry, Dr. Reddy. You are supposed to treat others, and I'm not supposed to make you a patient. Okay. They said, a star is a cloud that is heated by gravitational compression. Now, what does this mean? Just think of simple gas cloud. It's made up of matter. Matter attracts matter. That's what Newton said, because of gravity. So if there is a part of gas here, there's a part of gas here, it must try to come close. So, gas cloud must try to contract. And when it contracts, it applies a lot of, squeezes the center. Center becomes hot. So they said stars are shining because of gravitational contraction. Okay, then the question arises, okay, why does the star collapse and disappear? No, there is a problem. When the star is getting, the gas cloud is getting crushed and the center becomes hot, a hot gas tries to expand. That is the nature of a gas. So gravity is squeezing it and the heat is trying to push it. So there's a little bit of fight. And at the end, an equilibrium is reached where this balances the other. That is what you see here, this slide. This is gravity trying to squeeze. And this is what you call the gas pressure trying to push it out. And at some point, the whole thing settles down. And the gas as a whole has a pressure. And that pressure is made up of two things: the gravitational pressure and also the radiation pressure. Gas pressure, sorry, not gravitation, gas pressure. But the radiation that the star emits, that also has pressure. That was known. For example, when they launch satellites, it has large solar winds. And the light from the sun exerts pressure on the solar winds. So the satellite can go in all directions. So they have to have a very strong control on that to make sure the satellite goes in the right direction. It's like a wind pushing the sails. The light has got a pressure. Light can exert pressure. There's a long and short of it. So this total pressure is what balances the gravitational compression. That's what people said. Then Eddington in England said, let me imagine gas globules of different sizes. Say, 10 to the power of 30 grams, that's a very large number. 10 to the power of 31 grams, 32 grams. So he said, I will consider gas globules of different sizes and calculate the radiation pressure and what you call the gas pressure due to heat. And he did this. You may wonder, did the guy have nothing better to do? But he had a reason. Next slide, please. He did this for, gas globes of different sizes. This is a huge, 10 to the power of 40 grams is enormously different from 10 to the power of 30 grams. And you see the radiation pressure and gas pressure vary enormously. Here, radiation is small. Here, radiation is dominant. Here, gas pressure is high. Here, it's almost absent. And it's only in this band, it seemed that they could sort of be like stars. These gas globules will not be stars. These gas globules will not be stars. In other words, he said, for a gas cloud to be a star, its mass must be in a certain range. Our sun is one such star. We refer to the mass of the sun as a sort of a norm. We take the mass of the sun and say, we will measure all the other masses in terms of the mass of the sun. How many times? Is it 2 times, half, 4.5 times, 10 times? He said, well, it's in a small range. And the man who explained why it is in a small range will make his appearance in the next slide. This is Professor S. Chandrasekhar, one of the most brilliant physicists produced by India, but he spent all his time in Chicago. He came to Chicago and stayed there till his death. And he has made enormous contributions. Much as I would like, I can't go into that. But I can tell you one thing. JPL launched a satellite named Chandra from Cape Kennedy. And its job was to carry an X-ray telescope. and his wife Lalita Chandrasekhar was invited to that place to witness the launch specially. By that time, Chandrasekhar was no more. So it was Chandrasekhar who said, if a gas cloud has to be a star, the radiation pressure and the gas pressure must be sort of comparable. They must be in the same ballpark. Then they fight it out, and then somehow it's like a marriage where there is tension, but they don't get divorced. If one or the other dominates, there's a divorce. If the husband dominates, there's divorce. Wife dominates, there's divorce. So he gave meaning to Eddington's this thing. You just keep this in the back of your mind. And now let us go to the next slide. The next slide, there is a star here, Sirius. This is the constellation of Orion. It's called the Hunter, and this is the belt of the Hunter. And this is the eye of the dog star. The Hunter has got a dog, and this Sirius is supposed to be the eye of the dog star. Now, please note this Sirius, and we'll go to the next slide. This slide is important because in the year 1844, a very brilliant mathematician who was also an astronomer, he named Frederick William Bessel. Those of you who know mathematics will know there are things called Bessel functions. He invented the Bessel function or discovered them, whatever you want. He watched very carefully the orbit of Sirius, and he said, this Sirius has got a companion that is not visible. That took sharp mathematics. I mean, just by this has got a companion. There are many stars which are twins, and we can observe both of them. In this case, he could not observe the other star. But he said, I can tell you there is a companion. And he also said the companion, the orbital star, is about 50 years. He estimated that. That was the power of mathematics and astronomical observations. And it turns out Bessel was very close without any telescope and all that. I mean, the kind of telescope we have now. The actual period is 50.09 years, and he said it's 50 years. It's pretty good, I'd say. By the way, that companion has been found. If this is Sirius, this is the companion of Sirius. Here, you can hardly see it. This is a Hubble picture, and you can see how small this companion is. And this was disturbing the orbit of the other star, and Bessel was able to surmise it and predict there was a companion. Go to the next slide. This is important. Since the companion of Sirius could not be seen, they said it must be a very faint star. That's why we are not able to see it. And then they automatically assume that the density of that star must be very similar to Sirius. This was a very reasonable thing to do. And then they came to the conclusion that the mass of the companion star, companion of Sirius, was about the same as that of the Sirius itself. And so they said this companion star is just as big, but is very cold. Its temperature is very low, 10,000 times less than that of the Sirius. That is why it is not visible. This seemed a very elegant explanation. And next slide, please. Until in 1914, Walter Adams, using the Mount Wilson 100-inch telescope. Mount Wilson is somewhere in California. You're so close to the... Hey, I must go to that mountain. At least let me have darshan of the mountain. No, honestly, it's for astronomy, that was what you call something like Bethlehem for a long time. Many stars were born there, 200-inch telescope. It is very famous. Anyway, this is 100-inch telescope, and Walter Adams in 1914, using the famous 100-inch Mount Wilson telescope, he discovered that Sirius B was a white-hot star. Now, this was a puzzle. If it is as big as Sirius A and is white-hot, we should be able to see it. We can't see it. But this guy says it is the same temperature, it's white-hot. The only way to resolve this was to say it is small. That's why we can't see it. telescope. And next slide shows the Hubble picture again. There it is. It is just as bright as this, but we can't see it because it's small. And you need a Hubble telescope to see it. But if it is small and it has the same mass as Sirius, then density must be very high. Now, how high is the density? Next slide. This is going to shock you. 1 cup of Sirius B material would be the weight of about 25 elephants. And that was unbelievable. 10 to the power of, something like 10,000 grams per cubic centimeter. Uranium is supposed to be the heaviest element on Earth. It's about 19 grams per cubic centimeter. Water is 1 gram per cubic centimeter. Now, 1 cubic centimeter of Sirius B companies 10,000 grams. And one man said, nonsense. There's something wrong here. And that man, you will see in the next slide. That is Sir Arthur Eddington, who, by the way, was responsible for the famous experiment in 1919 when there was a total solar eclipse. He arranged for 2 expeditions, one to go to Africa and one to South America, to see the bending of light. Einstein's theory of gravitation says that light can be bent by gravity. Now, how do you make light bend by gravity? So Eddington said, very simple, you look at a star and then look at the light that goes past the sun. When it comes near the sun will bend it. And then you will know the star. When you see the star, it will be looking as though it is there because the light has come like this. When it comes near the sun, it is bent. So you will think the star is there. There's a problem. Sun is so bright, you cannot see the star in daytime. So Eddington said, no problem, wait for a total solar eclipse. The sun is black. Then you can see the star with a good telescope, and then you will see the light bending. Instead of being here, it will be here, and it's not there, but it's here. We know that. And from other astronomical observations, and from that you will know light has bent. So he sent 2 teams. In one place it rained. In the other place there was no rain. They got good photographic plates. They were developed, and in England he announced to the Royal Astronomical Society that Einstein was right, and overnight Einstein became famous. There are big headlines in New York Times and all that. By the way, there is another interesting part to this. Einstein at that time was in Germany, and between 1914 and 1918 there was World War I. Germany fought Britain. At that time it was under Kaiser. And in Germany, Einstein said, I don't believe in war. I am going to be a conscientious objector. I am not enlisting. And the law allowed that. So he continued to be a scientist. And in England, also there was this law that allowed conscientious objectors not to fight. Eddington said, I will be an ambulance driver. So he participated in the war, but as a compassionate serviceman. Nevertheless, he had read Einstein's paper, and he didn't care about the war. He didn't care about Einstein being a German. He said, this is a enormously important discovery. It must be verified. And even while the war was going on, because astronomers know when the solar eclipse is coming, total solar eclipse, he planned the entire expedition. And you see how war did not separate science. They were only interested in nature. Okay, one guy was a German, other guy was this. But it was good science and outstanding science. So this is the same Eddington. And he said, I won't go into the technicalities. He simply said, there is something nonsense because the star has to cool. It cannot be hot and that small. It has to expand. And if it is to remain that small, you are violating the known laws of physics. What Eddington did not know was that there was new physics around the corner, and that would explain this. And that new physics, essence of it, is illustrated in the next slide. Now, let us imagine the hydrogen atom is the simplest amongst atoms. And any time a physicist does a simple problem to represent a complicated problem, they will always say, let us do the hydrogen atom problem. If it is in economics, you take the simplest problem and call it the hydrogen atom. Toy model also they use. So this is a representation of a chain of hydrogen atoms. It has got 1 proton and 1 electron going around it. So if you put it in a line like this, as I told you this morning, the distance between protons is 10 to the minus 8 centimeters. The electron is tiny. So it's really emptiness. How come we feel a solidity? That was not explained by classical physics, but quantum physics explained it. It said, this electron you think is a small ball there, actually it's a cloud. So really speaking, a chain of hydrogen atoms is a cloud of electrons, cloud of electrons, cloud of electrons. You say, cloud means there must be a lot of electrons. No, it's one electron which has the probability of being everywhere. I know that's complicated, but that's quantum mechanics. But once you bring quantum mechanics and you put this electron like this, and you try to squeeze, the electrons will repel each other because the electron cloud in one has got negative charge. This has also got negative charge. Like charges repel. So when you try to crush it too much and bring this thing together, they become uncomfortable and they elbow you out. So there is a limit to which you can compress matter. And this was used by Chandrasekhar later on to say, when gravity tries to crush a star, at some point, matter will say, no more, thus far and no more. And that is when the quantum repulsion comes into picture. Eddington did not know about quantum repulsion, and quantum repulsion allows you to crush quite a lot before it stops. So in the companion of Sirius, what was happening was, quantum mechanics, which we thought was applicable only to an atom, was applicable to a whole star. It was trying to, it successfully squeezed it beyond the limits of classical physics, and yet allowed it to be a star. And so this is summarized in the next slide. This is the gravity crushes the star. Star becomes smaller, but then quantum repulsion sets in. Ultimately, there's an equilibrium. So when it settles down, it's much smaller than what it started with. And its companion of Sirius was really a highly squeezed star, but it was prevented by quantum mechanics from being crushed further. Now, this raised a question. What happens if the star is very heavy? Can it be infinitely squeezed, indefinitely squeezed to zero size? That kind of question arose. Next slide, please. That question was handled by Chandrasekhar. He was an 18-year-old in Madras studying there. He got a scholarship to go to England. He had sort of very interesting ideas. The theory given in England by Fowler by applying quantum mechanics was, well, it'll take a long time for you to really, this is mass of the star versus the radius. If you go to very large mass, it'll come down, but not dramatically. It'll take a lot of very heavy gas ball to get crushed, but then very heavy gas balls cannot be a star, Eddington has said. And he was thinking about all these things as, he has not even joined as a graduate student. And in the ship, in those days there were no planes, it took 15 days, he derived some results. And when he came to Cambridge, he was asked to be associated with a man called Ralph Fowler, who was also Dirac's guide, by the way. Dirac said, some of your results look okay, but some of it I think we have to look at carefully. Anyway, Chandrasekhar worked on it for 5 years. And then he derived this result, which is shown schematically. The essence of it is, if I start with a star of this mass, eventually, due to quantum repulsion, it will settle down to this size. But if I start with a mass, which is now called the Chandrasekhar limit, it will be crushed to almost zero size. Now, that is something that physicists don't like. They call it singularity. By the way, Chandrasekhar limit is 1.4 times the mass of the sun. So if a star started with an initial size 1.4, it stopped, radiating. That means no heat is coming, no radiation is being produced. Stars die. When it dies, it will be crushed to zero size. And Eddington, Chandrasekhar made the presentation at a conference in London. And Eddington, who knew about all this, tore him to pieces. He said, what nonsense are you talking about? What happens if the star is slightly bigger? You are talking nonsense. Actually, Chandrasekhar himself said something else would happen. But there may be other ways for a star to escape this destiny. And he gave a hint. But Eddington did not say anything. He just trashed Chandrasekhar. He was devastated. He comes back. He thought he was going to make an epoch-making announcement in London. He comes back, and then what happens? He stands there in Cambridge in the hall where he stays, looks at the fireplace. It started with a bang and ended with a whimper, he said. He wrote his thesis, got the degree, left England for good because of Eddington, came to America, went to Chicago. He accepted a fellowship there and stayed with the University of Chicago till the end. And Chandrasekhar limit is now accepted as one of the great discoveries of astronomy. In fact, he used to edit the Astrophysics Journal, and when he relinquished it, the press there gave him, University of Chicago press gave him a small farewell. And the guy, chief printer, said, we got a lot of papers about a thing called Chandrasekhar limit, but we don't know any limit to this guy. He was always working. Anyway, now, in the next slide, it just shows, if you start with a star mass, it will come to a certain radius. But if you start with 1.4, it will go to 0. That's what people said. Then said, what about stars which have a higher mass? What prevents a star from having 2 times the mass of the sun? In fact, we know they are there. What happens to them? That answer was not known, but Chandra gave a hint. Next slide, please. Chandra said, this is Chandrasekhar limit. I don't know what happens here, but in this range, you will get new physics. That's what he said. Now I will go fast. Next slide, please. This is situation in 1934. Up to here, you could explain the story of stars when they stop radiating. This gravity becoming dominant. Till then, there is balance. But once the star runs out of fuel, like a car runs out of fuel, gravity will start crushing. At some point, that crushing must end due to quantum forces. Chandrasekhar said the electron repulsion will stop it at this point, maximum. What happens here, nobody knows. Then Oppenheimer in California, 1939, in a very important paper said, from here to here, you will have neutron stars. What happens beyond? Now we know what happens beyond is the famous black hole. When a star is very massive, its ultimate destiny is to end as a black hole. So we sort of know what happens to a star ultimately when it dies. But very interesting thing is, before it reaches that, the stars also, like humans, have many births. Punarapi jananam, punarapi maranam, punarapi janani jatare sayanam shankara. That question was there for this astronomers. What are the different births that star takes? I will tell you that story. And there is a reason why I am telling all this story. And a tip of that mystery will be unveiled in the next slide. This shows Hans Bethe, born in Germany. He came to America because of Hitler. He was a professor in Cornell, and he was sort of officially Feynman's teacher there. But he was a remarkable man. And in 1938, Bethe attended a conference in Washington, D.C., at which George Gamow, who also came from Russia, actually Ukraine, I think. He escaped from there by a boat. He had a lot of problems and came to Turkey and then went through Eastern Europe to Germany and finally came to this country. He was very much interested in stars, and he gave a talk about what was happening inside the sun. How does sun produce energy? Previously, it was thought when you crush a star, it makes it hot. Like, you take a big gas balloon and try to crush it, it will get hot. They said Gamow said gravity is not the cause of heat production in a star. Star produces heat through nuclear reactions. Actually, Eddington was the first to say that. That was a major breakthrough. But Gamow gave more details. And then Hans Bethe, who attended that lecture, came out and said, let me think about it in detail. He did. And he wrote down all the nuclear reaction equations possible for the sun to produce energy, 1938. And one of them is a very complex cycle. Next one. I don't want to tax you with physics, but I want you to know what is called the carbon, nitrogen, oxygen cycle. You start with carbon and goes through a cycle and comes here. via many reactions, nuclear reactions. In the process, what happens is 4 protons become a helium atom. 4 protons combine to produce a helium atom. Hydrogen is the first element in the periodic table. At the end of this cycle, 4 hydrogens combine to produce a helium atom, which is the next in the periodic table. So a heavier element is born as a result of this. And in that process, a lot of energy is released. And our sun releases energy essentially by converting the protons into helium. That's the long and short of it. Please just remember that. Now, not only is a lot of energy, in other words, the fuel for sun is hydrogen. It consumes, and the emission gas is helium. What happens to that helium, I'll tell you in a minute. But not only is heat produced, not only is light produced, but there are some particles, mysterious particles called neutrinos, which I show here, neutrinos. They are very tiny, smaller than the electron, and very hard to detect. You can have hundreds of millions of neutrinos going right through the Earth without doing anything. They are the most elusive particles. And they will feature in the story very shortly. Just remember this, Hans Bethe wrote all these equations. How do we know this is true? These professors can be nutty, they can write down anything, but is there any truth to this? And the guy who set out to verify that, you'll see in the next slide. His name is Raymond Davis Jr. He was trained in physical chemistry. He worked during the Second World War on many problems involving physical chemistry. He did outstanding work. And then, much later, he said, I am going to set up an experiment to detect neutrinos from the sun. And he had a very good idea of how he was going to do it, because he was a chemist. And he set it up in South Dakota at a mine called Homestead. This is the surface of the ground, and his experiment was somewhere here. It's deep down. Why did he have to go deep down? Because, cosmic rays bring a lot of particles which are junk, as far as he was concerned. He went deep down so that all this junk could disappear, and he will get only neutrinos. Neutrinos can penetrate very easily. In the next slide, this is a big tank in the bottom of the mine, and here you can see 2 guys standing here. There's one guy standing here, there's another guy here, and there's a third person looking at this. It's a very big tank. And essentially, it had carbon tetrachloride. And when the neutrino interacts with the chlorine, it can produce a nuclear reaction and produce an argon atom, which is entirely different. In an entire year, he gets about 26 or 25 argon atoms. And out of this big tank, he was able to pick out that. He was so sensitive. And year after year after year, he was able to log this for many years. And eventually, when neutrino discoveries were celebrated, the Nobel Prize, he got it. He was the oldest person to have received the Nobel Prize. He was 84 or something like that when he got the Nobel Prize. So old people still have a chance. Now, I'm not saying me. I retired from physics long ago, or rather, physics rejected me. But the point I'm trying to say is, he was able to detect not only the neutrinos coming from the sun, but also raise a question, why is the sun not giving enough neutrinos? Because the number coming was less than what it was supposed to give. Has it gone to a secret bank account in Switzerland or something like that? And that had to be solved by an international collaboration in which the Canadians played a lot of part, but I won't go into that. I'll now very quickly go to the next slide, which is what happens. Here is the sun burning hydrogen, and all the hydrogen gets converted to helium. Then the sun stops burning. So when it stops burning, it starts crushing. Because, gravity takes over. And when it gets crushed, the helium starts burning. There comes a stage when helium becomes the fuel. You started with the fuel, and you got the exhaust gas, and then the sun stops burning. But then, after that period of quiet, there is gravity which crushes, and now helium starts burning. Can this go on? Yes. Next slide. You start in the sun with a hydrogen burning star, and after death, first death, it is reborn as a helium burning star, and then it is reborn as a carbon burning star. And how long does it go? It goes until the core becomes iron. I will show you what it means in terms of the periodic table. What I am trying to say is the elements that are in the body, that are in our Earth, were all produced by stars which were born and died for our sake. Because God needed, we need a lot of iron. If you want to build skyscrapers, you need iron. So he said, I'll wait for the humans. They are very greedy. Let me use the first generation of stars to fill the pantry. So now the question, okay, next slide, please. This is the core of a star, and in the core of the core you have iron, and all the other fuels, there are traces of this. This is like an onion skin. Next slide, please. This is another version. This is a 3D version. When you cut out, the iron is right here. Now this iron plays a very important role in what follows. Let's go to the next slide. This shows the periodic table. Hydrogen is here, and then straight away, yes, helium is there. Helium is there, then lithium, beryllium, boron, carbon, it goes like this. You may not be able to see it very clearly. All these are white, and these are in a different color, light blue. And these are in light yellow, up to iron. I will explain this light blue shortly. What I am trying to say is, starting from hydrogen, nature produces all these elements up to iron via stars. But on planet Earth, we have other elements. We have copper, silver, gold. We have uranium, which is here. And we have other things. Lead, mercury, rare earths, cadmium, zinc, all sorts of things on planet Earth. Where did they come from? By the way, these elements in pink, starting from here, are called transuranic elements, and they were made by humans. Actually, nature made them and they all disappeared very quickly because they don't live long. Humans created them in the laboratory, and many of them were named after humans or places. For example, this is americium. This is curium after Madame Curie. This is berkelium. This is californium. Your state has got its own element. And there is einsteinium, fermium, berkelium. There's somewhere, yeah, berkelium is right there. So, sorry, your university doesn't have, but Berkeley has got it. Harvard doesn't have one, by the way. So, man has been able to produce elements that are not found in nature. By the way, where did these come from? Let us follow that mystery. That mystery begins with this beautiful picture. This is called the Crab Nebula. And this Crab Nebula has a history that goes back to 4th of July in 1054. Long before you people started celebrating 4th of July, nature decided to have a 4th of July celebration in the year 1054. What did nature do? On that day, the Chinese astronomers noted that a bright star had appeared in the sky, which was so bright they could see it during daytime. In fact, they could see it for 23 days. They called it the guest star. And it was not seen in India because in India we have the monsoon. We had good astronomers. In monsoon time, you don't see the sky. It's mostly cloudy or rainy. But it was seen by Native Americans, and there are carvings in some caves which sort of mark this date. Now, they knew from the records of the Chinese astronomers where that took place in the sky with respect to the constellations. And when modern telescopes were built, they got a picture of what a big gas cloud, very big gas cloud, which is called the Crab Nebula. And after a lot of studies, they realized not only is the Crab Nebula the remnant of the supernova explosion that occurred in 1054 AD, because that's what it was. Supernova explosion means a star exploding as nothing can explode. It's really an extraordinary thing. I'm going to describe it very shortly. And then, after that explosion is over, that gas cloud expands, and this is that gas cloud. And right at the center of this, they were able to detect what is called a neutron star. Remember I told you Oppenheimer said there are neutron stars. They are all sitting in the middle of these galaxies that are the result of supernova explosion. Next slide, please. This is a picture taken in 1994. This galaxy is about 50 million light years away from us. That means light emitted from this galaxy takes 50 million years to come here. It's that far. And there was a supernova explosion, which was caught by astronomers in 1994. Now, you may not believe this, so I would like to show you the next slide. Actually, these are two pictures in one by the Anglo-Australian Observatory. This is the picture of the sky as it was in 1987. And look at this point. Suddenly, there appeared a big cloud. That means at this point, a star had exploded. And this is a picture taken later. This thing is there, but now a big ring has developed. The Crab Nebula is this thing becoming diffuse and this thing becoming thinner. So it looks like a huge gas cloud. So these supernova explosions do take place. Next slide is very remarkable. It shows an experiment in Japan, not very far from where the tsunami took place. In fact, this place was affected by tsunami. You see two guys here, Japanese. All these are what are called light detectors, very sensitive light detectors, photomultipliers we call them. There are thousands and thousands of these. And this whole thing is filled with very pure water. They were trying to detect something else. There is a similar experiment in this country somewhere. I think again in that South Dakota mine, it's set up there. But this was a much more powerful experiment. The Japanese put a lot of money into this. And it is taking data 24 hours a day, 7 days a week. Very good electronics, very good system. When in 1987, a supernova explosion occurred, they read, there is a thing called astronomical bulletin, and they read that this had occurred. So they very quickly went back to the data and said, our system can detect neutrinos. During a supernova explosion, neutrinos must be emitted. Has our system caught any? They went and looked at the data very, very carefully. Next slide, please. And they found that within a short period, this is 10 seconds, they were able to detect something like all these neutrinos, individual events. And there were 3 others also associated with this. 10, 11 neutrinos detected, and that got them Nobel Prize. And how many neutrinos entered the apparatus? 1 trillion. And how many neutrinos were emitted during the explosion? That is about 10 to the power of 60, if you can imagine. But I'll tell you this. In a supernova explosion that takes place in 1 second, the amount of energy is roughly equal to the energy which our sun will produce during its entire lifetime of a few billion years. All the energy that our sun pumps out in a few billion years, nature says, bang. That's really a big bang. And many stars explode that way. Okay, they explode that way. What's the big deal? And the big deal is the next slide. This may be disappointing, but notice all these elements are there. The yellow is what we had via stars. This is man-made, so we'll keep it apart. We'll take credit for that. But what about these things? By generating supernova explosions, a lot of, it's really a process where a neutron star is formed. A lot of neutrons are there. They interact with other nuclei up to iron, go through a lot of very complicated nuclear reactions. At the end of it all, God leaves you with gold, silver, platinum. You want platinum jewels? That's there. You want gold jewels? They are there. Silver ornaments? They are there. You want copper for your cables? They are there. Everything he provided. Because he knew humans would want all these things. So he waited and waited and waited. Produced a lot of these things. Okay, what happened then? When did we come? Next slide, please. This cosmic, if you look at the cosmos, there are places where there is what is called a dust cloud, cosmic dust cloud. These dust clouds really have dust left behind after supernova explosions and so on. And when they are big enough, they begin to contract, and then they begin to spin. So here you have a gas cloud that is spinning, and out of that spin, is born the sun and the planets. Yesterday in JPL, I saw a nice video of this. I mean, it's animated, this whole thing. And our sun was born about 5 billion years ago, roughly 5 billion years ago. 13.86 billion years ago is when the universe was produced. But God, Swami, waited for several billion years because, we want gold. Invest in gold. So he said, man wants gold. I'll wait. I'll create some extra stars, make iron. I'll make iron into gold via supernova explosions. I'll give them even uranium, cadmium, so that you can have your batteries. Most of our batteries in cell phones are cadmium batteries. They have also mercury. So he waited, and then he made the planet Earth as a part of the solar system. Let's go to the next slide. Planet Earth, let us say, was born there. This is time as a circular wrap. So he waited, and after some time, God produced very elementary form of life, whose job was to really produce a lot of oxygen. We have to breathe. So he make these microbes produce oxygen and create the atmosphere of methane and change it into oxygen. And then he allowed the fish to come. The fish appear somewhere here, and so on. This is about 5 billion years ago. When you come here, the numbers are there. I will leave the slide later on. And then here are the dinosaurs somewhere there. And we are just somewhere there. We are very, very recent arrivals on planet Earth. How recent? Next slide. Actually, the species Homo sapiens got perfected only about 100,000 years ago. And you will find that they were all in Africa, somewhere around Ethiopia. And from there, they began to move in different directions barely 70,000 years ago, which is nothing compared to the life of the age of our planet, which is about 4.5 to 5 billion years. And we are very recent arrivals. And the next slide shows the historic migration. About 100,000 or so, they went in different directions. And they came to Australia about 40,000 years ago. They came like this to this continent somewhere about 15 to 20,000 years all. This is how we speed. That is not all. The next slide, I want you to concentrate on this part. This is 10,000 years ago. Just 10,000 years ago. Jesus Christ came 2,000 years ago. Go back 5 times. This is it. That is when humans, domesticated animals, discovered, sort of learned to cultivate agriculture. And, fire was discovered somewhere here and so on. And we come to recent times, 20th century. In other words, all the progress that we have seen has really started happening just 10,000 years ago. What is that compared to the history of the universe, which is 13.86 billion years ago? God waited so long. But he waited so long because he wanted to put a lot into us. Krishna says, I am in you at 3 levels. Let us see some of that. Next slide, please. You may say, what has this got to do with God? Well, this shows the flexibility of the human body. No other creature on earth has got this kind of flexibility. Next time you go to the gym, just pause and thank God that you have this flexibility. The giraffe may be able to just stand up and eat. The elephant may be able to pull 10 cars and crush it with 1 foot. But at the end of the day, our body is more flexible than even the cheetah. Cheetah can run very fast, but we can do a lot of things. And that's because of the power of God in us. You don't believe me? Take a look at the next slide. Here you see a ballet dancer. Next slide. Here you see a Bharatanatyam dancer. Look at the pose. There's flexibility. And now, I like sports, so go to the next one. Here's this guy balancing himself, tennis match. I don't know who he is, but he really has the flexibility. Next slide, please. This shows my love for cricket. You know, all of us Indians are cricket crazy. And you may not think there is much of flexibility, but in order to play this shot, which is a cover drive, he has bent backwards and forwards. Next slide, please. This is an Australian chasing a ball and trying to catch it. Look at the flexibility. And next one. Again, cricket. Here's this guy trying to break his head and he's ducking. Flexibility. Next slide. This is different. You look at these fingers, 10 fingers. I'm told 1/3 of the brain is reserved for controlling these fingers. We don't realize what power God has put into these fingers. Newton said, the thumb alone is enough to prove that God exists. Who is this? Isaac Newton, one of the greatest scientists of the second millennium. And you know, if you take this bottle, I can open it just like this. You try to do it 4 fingers. You can't. No animal, including chimpanzee, can open a bottle. God is in you. We just don't take it as an abstraction. That is in us at all these levels. Next slide, please. This is, I think, called the Titan. It is the world's most powerful supercomputer. It's in Oak Ridge, Tennessee. Right now, this is the most powerful supercomputer. And its power is that of 17 million pieces. And pieces these days are quite powerful, 17 million pieces. It consumes 15 megawatts of electricity, which is what probably a small town in this country consumes. And it has all sorts of what you call records that we can talk about. But I don't want to dwell too much on this, but I want to show you something else, which is in the next slide. Okay. Just a second. This slide shows the human brain. It weighs how many? 3 pounds? 2.5 pounds or something like that? I don't know how much, roughly in that range. And this beats hollow any supercomputer that can build. In fact, it is this that builds a supercomputer. It's actually a quantum computer and a supercomputer. I won't explain the mysteries of quantum computer, but the essence of it is it can do hard problems in a very unique way by taking shortcuts. And just to give you an idea of that, let me show you the Rubik Cube, which was a sensation many years ago. This is a typical random configuration of the Rubik Cube, where every face has got all sorts of colors. And this is the ideal where the red is all on one face, green is one face, blue is one face, white is on another face, and all that. So in the first World Rubik Cube Championship in 1981 in Munich, the winner went from here to here in 38 seconds. Okay, so what's the big deal? This is one of the 40 into 10 to the power of 18 possibilities. If I turn this, I can do that in 40 into 10 to the power of 18. 10 to the power of 18 is 1,000,000 trillion. Out of that, that is the correct answer. And that is less than a needle in a haystack, and this guy did it in 38 seconds. Now that has been lowered. How did he do it? People have all kinds of ways of remembering this and that. But that's because the brain is a quantum computer. And God has put enormous power into our brain. Just look at the developments, technological developments. Somewhere around 1895 or somewhere thereabouts, Bell invented the telephone. He called Thomas Watson, who later founded the IBM. He was in the next room. He said, "Mr. Watson, I need you. Come at once." That was the first conversation, very famous. In 1926, they laid a first transatlantic telephone cable from New York to San Francisco, and there was Watson. And Graham Bell rang and said, "Mr. Watson, I'm here. Come at once. I need you." And Watson Riley said, "Yeah, but it'll take me 4 days." By that time, the transcontinental railroad had been built. It had actually been built in Lincoln's time. So, we have this enormous, beautiful body, which has got so much flexibility. We have these fingers, which have so much power. We have got God-given brain. God is in all of them. Why did God give all these things? When God says that, listen, buddy, I built this temple for myself. I'm going to go and sit in that temple. Install me and worship me. Instead, what does man do? He spends $100 million and builds temples in concrete and stone. God, you come to me. God says, why should I come to your temple? I got my own temple, man. Just put me there. It doesn't cost you a buck. You got $100 million bucks. Use it for my jobs. There are a lot of poor people. That's all me. Feed me. We don't realize that. By the way, let me show you the next slide. You know, memory sizes have been coming down and down. You know all that. Hard disk today. A few years ago, the computer had the PCs had a memory of, made by Seagate, about 2.2 GB. In our hospital in Puttaparthi, we had a computer which is connected to the gamma camera. It is 2 GB. That failed. And we went to the Siemens to replace it. They said, no, we have to replace the whole computer because 2 GB disks are not, hard disks are not available. Our engineer was smart. His name is Sri Krishna, by the way. He went to the junk store. He found an old PC with a 3 GB and brought it because, you know, the cost was something like 15 lakhs. He just took it out of the junk. Luckily, it recognized and the gamma camera is going on. Now, I mention this because very recently, a British scientist made a memory out of synthetic DNA. Because DNA is very efficient in storing energy, information. So they said, let's create a DNA and put information in it. What did they put there? They put Martin Luther's audio clip of Martin Luther King's I Have a Dream speech, a photograph of Francis Crick and James Watson's famous double helix. They made a model of that. And 154 sonnets of Shakespeare. So all this was put and they were able to play back and it was in a test tube. Of course, very soon, in another 15 years, you will have DNA memories replacing all your current solid-state memories. Human brain is able to do that. That power God has given us. And the question before us is, are we realizing the power God has put in us? And I would like to end with the next slide because this clock is really moving fast. I think there's something wrong with it. You see an iron safe with gold in it. This is, of course, a graphic which we created for this talk, especially. But it relates to a discourse that Swami gave, the hidden treasures within us. I'll be playing that discourse down the tour. I call it a discourse walkthrough. And there he says, oh man, you do not look inside. You are only looking at this iron safe, which is your body and mind. But you know, iron safe is not so valuable as what it contains. No safe is very important. It's needed for protection. It contains all jewels. I have put all those jewels. You are not looking at it. Instead, you are admiring the safe. Look at them. What are they? Human values, including daya, karuna, and he compares it all. And then he says, when you walk on the beach, you get shells. God is smart. The ocean is smart. It knows you want only junk, so it gives you only the shells. The pearls it keeps. It doesn't give. And then Swami sings the line from Meera, which he often film Meera, sang by M.S. Subbulakshmi, which he often used to sing in his discourses. Kadalil kulittor muttaditene kainalvo viduvayo giridari gadilen giridari. Swami breaks down. Meera says, I dived deep into the ocean and got a pearl. That pearl is you, Krishna. It is trying to slip out of me. Will you allow it to happen? What will happen to me? Please help me to hold on to that pearl. He says, you must ache for God like that. I put the treasure. Open your heart and take that jewel, scatter it, and spread love. That is what God wants us to, but somewhere along the lines, we have lost our way. Our GPS system did not work. What went wrong? How did we lose our way? That comes in the next episode, brought to you by Radio Sai. Tomorrow.